If I didn't forget it now, I probably forgot period 2, so they're still going to page me. Anyway, okay. So why do we have a circulatory system? We have a circulatory system to move stuff around the body. So we have a circulatory system just to move stuff all around. And all the stuff we want to move, it moves. We want to move waste around, it moves waste around. We want to move nutrients around, it moves nutrients around. We want to move messages around, it moves messages around. It's a regular old postal service, your circulatory system. You put it in a box and ship it, and it goes where you want it to go, kind of. But the most important thing of all is oxygen. The most immediately necessary thing to every cell in our body is always oxygen. Smaller cells just allow oxygen to flow into them. Single-celled organisms, oxygen will flow across the membrane. As long as they're in a place with oxygen, because things naturally flow from where there's lots to where there's little, a cell out in nature, as it uses up oxygen, oxygen will naturally flow into the cell. Does that make sense? So if you're a bacterium, you don't need to worry, oxygen will make its way into your cell. Does that make sense? And even really small animals. A lot of insects don't have much in the way of circulation at all. If time permits, at the end of this unit, we're going to do a grasshopper dissection, which is a real departure from doing the bigger animals. But you'll see their structure is very different. Do grasshoppers have lungs? No, they don't need them. They can use different systems. But we do have lungs. In mammals and in many large animals, well, in all larger animals, O2 is brought to a central location and then spread throughout the body. This makes good sense because the parts of your body that are deep inside the body would have a tough time getting oxygen, right? If we just absorbed oxygen, our skin would get a lot, and our heart would get very little. And our brain would probably have a hard time getting oxygen because it's surrounded by your skull, right? This does not seem like a good system. I suppose we could drill some holes in our skull to let the air in. This also seems like a bad idea. Yeah.
I can't see what that word is next section.
Place. Sorry. I'm sorry. No, anytime. Please ask. Okay. In mammals, and many others, but we're going to focus on mammals for the moment. In mammals, this is the lungs. By the way, it's also the lungs in reptiles and lots of other things. What's an example of a larger animal that doesn't have lungs? Some very large animals in this category. No, whales have lungs.
Oh.
Whales are mammals. Whales evolved from land walkers. They moved back into the ocean. They're actually not very closely related to the answer I am looking for, which is... Come on, guys. Big animals that don't have lungs. The shark would be an example. Yeah, fish. Fish don't have lungs, right? What do fish have? Gills. Whole different system.
That's so honest.
That's okay. Don't feel stupid.
I was thinking about it, but then you said it's not related.
I'm making you feel stupid.
I thought you said that.
You really said, come on, guys.
I didn't say like, come on, idiots. Oh my God, you're so stupid. I can't believe you didn't know that. I was being encouraging. I was saying like, come on, you got this. You got this. That was like a...
Are you that dumb? You don't know?
No, I would never. Would never. I talk about that when we ask about like what you've read, but not about, come on now.
So how would you say they're much bigger and unrelated to whales?
Because they're not, a whale is much closer related to you than it is to a fish, which is an example of something that seems counterintuitive, right? At first glance, you'd think whale, that's a lot like a fish. They got fins, they got flippers, they swim in the ocean. But actually, whales evolved from a common ancestor of us that made its way back into the water and evolved some fins, some flippers, and started swimming around. But yeah, they're mammals. They give live birth. They nurse their young. They have lungs. They have to come up to breathe. Yeah. Jellyfish are not actually fish. We call them fish, but no, they're not actually fish. They're a whole different category. Yeah, they're weird. I don't know much about. That's a portion of the animal kingdom tree that I know desperately little. I'm real stupid when it comes to that stuff. I learned a bit this year because I got a wonderful project on jellyfish. But yeah, not something I know a lot about. So what we want to do is this. Blood flow is a circuit, right? We talked about this already. And it's a circuit to allow for constant replenishment of oxygen. I.e., really, in the end, your blood has one goal. It needs to go from the lungs to everywhere else. So it needs to take oxygen to everywhere else, and then it's going to bring back a waste product that we need to get rid of.
What are the last words on
Replenishment. I'm sorry, that's... What does it mean to replenish something? That's like a $1.50 word. Yeah. Refill. Refill would be a great word. Absolutely. Right? If you're working the buffet and your job is to replenish it, your job is every time somebody's hitting those Swedish meatballs hard, you gotta keep filling up the Swedish meatball station. It's important. Oh, you go to the buffet and the Swedish meatball station's empty, you're gonna make people angry. You don't want that, right? I love a buffet. God, I love a buffet. I get, I think for some people a buffet is intimidating, and for other people a buffet is exciting. And I am one of these people.
It's intimidating to you because it's like people are just gonna watch a big battle.
And can I tell you something else? And I feel judged at a buffet? A little bit, because I understand I'm putting a lot on my plate. I don't need your eyes to tell me that, all right? I get it, bud. You take care of your plate. I'll take care of my plate, all right? Person I've never met judging me at the buffet, but I can live with it because I love the choice. And you know what I miss? Oh, salad bars. See, when I was a kid, so many restaurants had a salad bar, which is where, even if the restaurant didn't have a buffet, there'd be a salad buffet that you could go to, and you could, all the stuff you could put in your salad. Oh, it was so good. And you could just go up as much as you wanted. Right? You could have 11 salads. Nobody could stop you. And you know what's funny? Nobody judges you at the salad bar. You can load your plate up like this with salad. Nobody's like, oh, look at this guy. But you load yourself up with the Swedish meatballs at the buffet, and people look like, oh, what's wrong with this guy? And it seems like a double standard to me. That's all I'm saying. That's all I'm saying. Double standard.
At a buffet, you make sure you eat your money's worth.
Right? That's what I'm saying.
Actually, I would never go to a buffet because I know for a fact I'm not going to eat as much as I've paid for.
Well, let me tell you. I'm getting my money's worth. Buffet sees me coming, and they go, we better get some skinny people in here to make some money because this guy's getting his money's worth. Yes.
I have a specific question about how do they figure out how much to charge you? You know what I mean?
Can I tell you? I'm not going to answer that now, but I have in fact developed a very carefully built equation to figure out exactly that. Because I'm serious, because it's a big deal in a restaurant. How do you figure out what to charge for things? Especially something that's all you can eat, right? You got to make sure you're making your money. And the answer is a lot of research, and you have to know your food costs, and then you have to have done market research to know how busy are we going to be, how many people are going to come in, and then how much are they going to eat on average, right? And it's interesting because it very much changes depending on what you're offering. So if you offer the kind of stuff that stereotypically appeals to a bunch of hockey playing guys, coming off of a night of just playing 3 hours of hockey, they come in and they're going to demolish your buffet, right? And then on the other hand, if you're getting just the general public at large you're going to get something, a lot more kind of just middle of the road, right? And then if your buffet is, I'm trying to think of an example of people who stereotypically don't eat much, like, I don't know, like health nuts. Like if you went to like a, sorry? Small people, yeah. No, let me tell you something about small. You cannot assume. This is something you need to know too. Like, listen, I am like the size I am, and it is actually incredibly independent of how many calories I put in my body. I've been on a 1,200 calorie a day diet, not a month. That would kill you. I've been on a 1,200 calorie a day diet, and like my weight does not move 1 ounce because your metabolism is just like, not giving us much food. Better get every last calorie out of all the food we eat. And if I start putting a lot in, like it'll be like, it's okay, we can let some of this burn. Like looking at somebody's size and predicting from that how much they eat is actually really ineffective. And let me tell you, somebody who manages restaurants, I can tell you that for sure. Like there's some little people who can pack food away, right? There are. And then like it is not a prediction. So that's something you should know. And it's also something you should keep in mind when you're, next time you're judging somebody at the buffet loading the plate up with Swedish meatballs.
I don't trust the hygiene of other people to eat at buffets. I don't trust that they're not.
Can I?
Like people are absolutely sneezing in that food, and I don't appreciate it.
No.
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 Some people don't cover their face when they sneeze.
No. Well,
I hope they at least turn away.
My mom once
Yeah.
found a
And look
Band-Aid
at
in one of
buffet,
the
we're
food
talking
plates
like
in
the
the Mandarin.
Mandarin. There's no way we're gonna let people like eat food that's like not sanitized and cooked by like untrained
Yeah.
people who are
Yeah.
business.
But you're worried about the public. You're worried about the public? Because to be clear, any restaurant you go to, people are handling your food in the kitchen, right? Like, just so you know that. Like, you may not see it, but like, there's still people handling your food.
No, but it's the people.
And in a way, a buffet or like one of these places that has an open kitchen, at least like they know people are watching, right?
Yeah.
There's an advantage there. Like there, like everyone can see what's going on. Yeah, you go to the Mandarin, like they're not going to let somebody like, sully the food and then just like not do anything about it because it's in their business interest to have people not be like grossed out. Anyway, I'll tell you something else. I can't speak for everywhere. I've only worked in the restaurants I've worked at, but I worked many, many years in the food industry, and I never once saw somebody in the kitchen do anything inappropriate to food. And if I had, like, I'm in management, like, A, they'd have been fired immediately, and B, like, I've just never seen it. And I'm sure it probably happens in some places, and may those people be fired today. Anyway, okay, so from the lungs we take the blood everywhere else and we deliver precious, ever important oxygen. And then the blood's going to go back to the lungs and it's going to get rid of something it picked up everywhere else. That is, we're constantly getting rid of. Carbon dioxide, good. And this is the cycle. Blood goes to the lungs, gets rid of CO2, picks up oxygen. So keep in mind, we're constantly breathing in oxygen, and the lungs are constantly breathing out carbon dioxide. Does that make sense? Of course, the main problem with this is that this can't be a full picture, because how does the blood get from the lungs to everywhere else and from the everywhere else to the lungs? And the answer is it needs something in the middle, and what it needs is so important in life. You gotta have heart. You gotta have heart. You gotta have heart. Both literally, because without a heart you'll die, but also figuratively, because it's important to be a soulful person. We're man does not live on bread alone, as one might know. So let's slightly modify our diagram, because blood can't just go from the lungs to everywhere and from everywhere to the lungs. So what does happen? And the answer is kind of a figure-8 pattern. So first we're going to draw this very much we're going to draw it in 2 steps. Step 1, we're going to draw it very simply. And in the very simple diagram is a slight modification. We have the lungs, and then we have everywhere else. And in the middle we have what? The heart. And what happens is the O2 is going to come into the lungs, and we're going to put that in the blood, and we're going to send it back to the pump. And the pump in this case is the heart. And then where is the heart going to send it?
Everywhere else.
Everywhere else. And then from everywhere else, it's going to make its way back to the heart. And then the heart will send it back to the lungs. And from there, the CO2 will be breathed out. Does that make sense? I'm going to make that a little prettier. Okay. And there's actually some very simple animals that actually have a heart that really does work like this. Of course, the problem is if the heart was just one big chamber, what would happen with all the blood that had oxygen and all the blood that had lost its oxygen? Every time it got to the heart, it would mix. And for some small animals, that's exactly what they do, and it works fine. The heart is just a big central place, and the blood comes into it, and it squeezes and it pumps it out, and half of it goes everywhere, half of it goes back to the lungs, and it always keeps the oxygen level kind of middle. Does that make sense? But our oxygen needs are much higher than that. We're bigger, we're complicated, our brains use a lot of oxygen, our muscles use a lot of oxygen. So for us, with a system this simple, we would always be mixing oxygen-rich and deoxygenated blood. So with a one-chambered heart, oxygenated blood and deoxygenated blood would always be mixing. And again, you can get away with that if you're very little, or if you don't use a lot of oxygen, if you're a pretty sedentary animal, and you got a small little brain that doesn't do much, and you've got a low metabolic rate, but we don't. We have a very high metabolic rate. We're constantly using oxygen. So oxygenated blood and deoxygenated blood would always be mixing. How do we prevent ours from always be mixing? Do we have a one-chambered heart? No. We do not. How many chambers in our heart? No? Four. Anyone work with engines? We got any gearheads in here? Any grease monkeys, as they call them? Ever heard that before? That's what they call mechanics. It's a derogatory term. I wouldn't, but grease, yeah, they like engines. Anyway, if you work with engines, you've always got your inlets and you've got your outlets. You want a place where the gas comes into the engine, and you want a place where things go out. So we have a four-chambered heart. And so here's our slightly modified diagram. We have the lungs. We have everywhere. And then we have our heart. And our heart, we're going to draw for now as four chambers. We're going to keep it real schematic-like. And we have the chambers up top, which are called, this is like a hotel term. Does anyone know what you call like the open air above the lobby of a hotel lobby? The atrium, right? So we call the tops the atria. So A for atrium. And of course, it goes without saying that this is the left atrium, and this is the right atrium. Right? Is that correct? Very good. Very good. Look at you guys. This is correct because... I kind of want to stand in front.
You don't need the chair. It's okay.
I do. Now somebody go scroll. I need you to put that on my chest.
This is so not smart.
I don't think that's gonna.
Did you just call me not smart?
I said this is so not smart. I didn't
This idea is this.
Okay, put my heart in.
That's
There we go.
perfect.
See? That's perfect. See, and you doubted me. So if you look, for me, this is my right atrium.
If you fall, I'm gonna laugh at you, Mr. Orlando. I'm not gonna lie to you. If
If
you fall, I will laugh so hard. I'm gonna laugh so
Can
hard.
I tell you, I used to be so spry. I used to spend my whole day teaching just standing on tables, and I'd hop from table to table.
You told us.
I've gotten so old and fat and lazy, and I just don't anymore. And now I stand on a chair, and they're all like, "Oh my God, he's gonna die!" I mean, relax. I've stood on a chair before. Said Orlando right before he fell and died. He'll say nice things at my funeral, right?
No.
It doesn't have to be true, just like my family. Like say some nice stuff. Like he was really good. He was good. So anyway, take a look. So up here, my right atrium. Now, when you look at my right atrium, you see it on what side? Left. And when you look at my left atrium, you see it on your right side. That's right. So,
I saw someone pull up the L's. I was going to lose my.
so we call this the anatomical position, which is, you always imagine the anatomical position in this very specific pose, just like this. Right? See this? You always assume when you're looking at a diagram in biology that the person you're looking at is standing in front of you, upright, with their palms supinated, which just means that the palms are facing towards you, which means like the thumbs should be out, right, and the pinky fingers in. And any drawing we ever do, you imagine that you're looking at a person, which means if I'm looking at you and I'm looking at my right, I know that this is in fact your left side, right? And this is your right side, right? I look at you, that is your left side, that's your right side, right? Because it's the opposite of mine. Can we keep that in mind? So, this is important because the left and the right side of the hearts do very different jobs. So, the atria, in fact, I'll say atria because the plural of atrium is atria. So, and V is for, and I'm going to change the color on this so that it isn't color-coded. V is for the ventricles. Good.
Wait, they have to be colored or?
Well, you're going to see my color scheme in a minute. Oh, see, I just almost did it, and you will almost do the same. This is the left ventricle, and this is the right ventricle. Now, why have I color-coded these? Well, like we said, does blood actually turn blue without oxygen? No, but it does turn bluer, and mildly. It is a small difference in color. But the molecule hemoglobin is what gives blood its red color, and it slightly changes colors. Its pigmentation slightly changes depending on whether it's stuck to an oxygen or not. So the convention then is we show oxygenated blood in red and we show deoxygenated in blue. Again, cannot stress enough, at no point is your blood actually blue. All right? We cool? But again, what it is it is bluer. It's bluer. All right? So, what happens is this. We have to start somewhere, so let's start at the lungs. Because at the lungs, O2 goes in, right? And then the blood, full of oxygen, is going to go out, and it's going to go into the heart, and it enters the heart at the left atrium. And then it's going to flow down into the left ventricle. There's going to be a valve there. And what's the purpose of a valve? There's a valve here too. What's the purpose of a valve? What does a valve do in something? Yeah, you can close and open. And there's different kinds of valves. Like every faucet is a valve, right? It has a ball valve inside of it. And when you open it, the water can flow through. And when you close it, the water can't. The valves here are one-way valves, which means they always let blood flow one way, but they will stop it if it flows the other. And when we dissect the heart, you'll actually see how that works. So is your question, are we going to dissect a specific person's heart? No, we're not going to do that, of course, right? Because that would be ridiculous. Anyway, let's get back to work. Come on now. Okay, so whose heart? So then, from the left atrium, the blood's going to flow down to the left ventricle, and from there, the blood is going to go everywhere. It's going to go every single place in your body. And of course, when it does that, the O2 is going to go in, right? That's the point. Every cell in your body needs O2, right? And by the time the blood comes out, what is true? Yeah. And in addition, it has less oxygen. Now, by the way, we've already said, does it have no oxygen? No, but it has less. But in addition, what has gone into the blood? Carbon dioxide. Now, that isn't going to go to the right ventricle. It's going to go to the right atrium because the atria is where blood is collected. All right? You enter through the lobby. In this case, blood comes in through the atria. From the right atrium, where is it going to flow down to? The right ventricle. And that's going to come out. And I don't have a good way to draw this, so I'm just going to kind of do this. Be like, whoa, oh, slides over here. Does that make sense? Like, oh, look, it slid over top of that. That's, whoa. Okay, there we go. Because you got to kind of somehow show that it's going to make its way where? To the lungs. And in the lungs, of course, we're going to breathe out the CO2. And what are we going to do? We're going to get rid of the CO2, and we're going to pack it up with oxygen. Good. Yeah. Can you which? Am I in the way? Oh, sure. Yeah, of course. You don't have to ask me that. You guys are big kids. trust you to manage your fluid intake and outlays all on your own. Really, I would like to have nothing to do with managing the fluid flow into or out of your body in an ideal world. That's what I think saying in my business, you know? I would say it's kind of weird. Like, it's part of why I have no interest in being like an elementary teacher. Like, I even hate grade 9 because there I do have to be like, you have to ask me this or that. But you know what I mean? Like, I don't, like, it's weird. Can I go to the bathroom? I don't know, can you? And then they say like, well, may I go to the bathroom? And even still, it's like, why is that up to me? Like, if I say no, like, do you have to sit there and like just pee yourself? Do you know what I mean?
Yeah.
Do you see what I'm saying? And again, I get why teachers, like, don't get me wrong. I think that elementary kids should in fact have to ask to go to the bathroom because you can't trust them. They're wild animals. Like grade 9s, you can't trust them. They're little mutants, little gremlins. You trust them. You leave right. You let them do what they want. They'll bust up the joint. But you guys are grade 11s, grade 12s. By now, you should be able to handle these things on your own, don't you think? And to me, if a kid's causing a problem, then rather than punishing everybody, you get some bigger kids to beat that kid up and then tune them up, and then they'll know better. Of course, I'm joking. I would never do that. I would obviously handle it in a mature manner by following the proper ladder of intervention. Yeah, exactly. So I'm making it very clear that what I would actually do is follow school policy and just handle things in an appropriate manner. And I would never in a million years handle things by encouraging one student to engage in vigilante justice against another student to make them behave properly in my classroom. That would be ridiculous. Instead, what I would do is just follow up along the appropriate channels and engage in proper school discipline. All right, moving on. I feel like I've covered my bases. Right? It's a good looking diagram. So there we are. This is how blood flows in the body. And the important thing to remember is it's a circuit. It's just a big figure 8, right? We go to the lungs, we get blood. We go back to the heart. We go everywhere else, we drop off the O2. We go back to the heart. Then we go back to the lungs, back to the heart. Everywhere else, back to the heart. Back to the lungs, back to the heart. Everywhere else, back to the heart. It's a big circle. We bring oxygen from the lungs, we come in on what side of the heart? The left side. And from everywhere else, we come in on what side? The right side. So the left side of your heart has to pump blood everywhere. Your right side of your heart only has to pump it to the lungs. Which side must be stronger? Why does the left side got to be stronger?
Because it's not to everyone.
Yeah, especially when you think like where the heart is, right? If you look at where the heart is, it's here. The lungs are right nearby, right? I mean, the lungs are just, I don't want green lungs. That feels weird. The lungs are like right here, right? So the distance from the heart to the lungs, pretty small, right? So the right side of the heart, much, much, much less robust than the left side of the heart because the right side of the heart doesn't have very far to travel. Does that make sense? So we can make a quick note about that here, and then we're going to learn all the proper names for all the structures of the heart. So the left side of the heart is much stronger. It has to pump blood everywhere. No, not pump. Man, you know what a weird word is when you say it, thinking about it? What? Pump. Say it a couple times and really think about what you're doing. Pump.
No.
Pump. Like any way you say it, it's weird. Pump.
What is happening right now?
I'm saying the word pump and I'm thinking about it. Because I misspelled it as pum, and then I fixed it to pump and realized that's still a ridiculous word. Any other questions?
Like plotting.
Let's change it? I don't know. Squeezy pushy thing.
Okay, yeah.
Yes, that's a bracket. I'm sorry. I think at some point somebody built a thing and it moved stuff by like squeezing it or pushing it, and he was like, what are we going to call this thing? I don't know. How about pump? Like, who's this guy? It's a guy. Do you see what I'm saying? Like, we take it for granted, but somebody named that. Was his name Pump? Was it like Larry Pump and he built this thing and he was like, I'm naming this after me? I don't know. I don't know the etymology of the word pump. Now I want somebody to look up the etymology of the word pump, but not right now. Does everyone know what etymology means? Not the definition, but the history, right? So like Yeah, the etymology of a word is how that word came to its current usage, right? And often in English cases, it comes from either Latin or Greek or from from sort of Old English. But Pump, I don't know. It could have been a guy's name. It could have been Jimmy Pump. Or maybe Pump was his first name. I've never met a guy named Pump, or a girl named Pump for that matter. But like, you can name your kid that. Who's going to stop you? Pump Novak?
I would name this kid like
They could call him Ump for short. I don't know.
I feel like you'd be classified as a bad parent.
Do you think you end up on a list if you name your kid Pump?
Yes.
Like, is that an automatic call like to some sort of children's aid society where they keep an eye on you? Because like rich people can get away with stuff like that. Have you seen the things rich people name their kids?
Yeah.
Like bonkers stuff, right?
Shut the hell up, Angela.
Whoa, wow, whoa, boy, wow, we're getting harsh. Jeez Louise. Golly gee gosh. Okay, now I want to look at the heart and look at the actual structures, but as we're doing so, listen. Don't try to memorize all the structures of the heart. Tell yourself a story. Shut up, you. Golly gee gosh. Novak, could you like give him a really hard time for a minute or something?
I have been. I actually slapped him earlier.
Okay, good. Okay, obviously you shouldn't do that because that's violence and we don't believe in it. And it's important to me to understand that we handle our problems with our words, not with our fists or open hands, as the case may be. Okay, so let's take a look at this. This is your heart. Now, obviously, this is still just a drawing. You're going to see when we go to dissect the actual thing, boy, is it like kind of just a whole bunch of tubes turned in on itself. It's hard to see, but this is the basic layout of the heart. And there's a lot going on here, right? So let's get to it. Because we said this side is the left side and this side is the right side. You don't need to label that, but just that's going to help us as we go to make sure we don't screw up. Because if you look, there's chambers that mirror each other. Up here we have an upper chamber, and over here we have an upper chamber. Those are the atria. So this is the left atrium. Fun fact, left has a T at the end. And this is the right atrium. And I am going to make life simple, kind of color code things. I am going to use blue for... Oh, I'm sorry. That is pointing to that. Yes, that is the right atrium. Sorry, I just assumed they'd be on a line with each other, which they should be. Okay, I'm going to use blue to show chambers of the heart. Does that make sense? Now, let's go on a journey. Let's say we're blood. We're coming in through the left atrium. We just came from where? The lungs. And we came from the lungs, so we must have come in either from the left lung, and if we did, we're going to come from the left lung vein. Only we have a Latin word for lung. Does anyone know the Latin word for lung?
You do.
I do, that's true.
No, there's not.
I'm going to see if somebody can get.
Pulmonary?
Pulmonary. Very good. See, you did. So all that means is lung. So these are the veins that come into the left atrium from the left lung. These ones here sneak their way around behind and they get there as well. Do you see that? Because this isn't a 3D model, you can't see it. But these two here go all the way to here. These come not from the left lung, but from the right lung. And so these are the right pulmonary veins. And again, pulmonary just means lung. So if you're blood, you've just come into the left atrium, and you either came through the left pulmonary veins from the left lung, or you came in on the right pulmonary veins from the right lung. Does that make sense? So we're going to add another thing here, which is we're going to use this color here, IM, for blood vessels. All right? And we're hopefully going to be able to help sort this thing by there. So I'm blood, I've come in from the lungs, and now I'm in the left atrium. Where do I need to go? I'm going to go down. And I'm going to go down into this chamber here, which is, what is that chamber? It's the left ventricle. And blue is my color for chambers, right? Now, this looks like it's pointing to like this kind of towery thing there, the thing that's holding the fibers, but we're just going to be talking about this chamber in general This is the left ventricle. The atrium is where we collect blood, but the ventricle is the part that actually does the... What's the heart for? It's a pump. And look at the walls. See how thin the walls of the atrium are? Is that going to be an effective pump? No, because what are the walls of the heart made out of? What's all that? That's all muscle, baby. And when it contracts, the blood flows. So, is this going to be an effective pump? Absolutely not. But this is big, thick muscle tissue. And you're going to be amazed when you dissect the heart how much of it is muscle and how little of it is open space. So that's the left ventricle. But we need to make sure when it pumps, where don't we want it to go back to? We don't want it to go back up into the lungs. So we have to have something to make sure it can only go one way. We want to make sure blood goes this way but can't go back. So we need a valve. All right. And we're going to learn 2 sets of names. Today I'm going to teach you the better set of names, and tomorrow we're going to learn the other set of names. We're going to call this the left atrioventricular valve. That's a good name. No, it's a good name. What does this do? It's on what side of the heart? What 2 chambers does it separate? The atrium and the ventricle. And what is it? It's a valve. This would be like if I had named my son firstborn male child Orlando, born in 2005 on December 25th, so I wouldn't forget his birthday. See what I'm saying? Like, that's a descriptive name. Don't worry. Does it also have a stupid name that you have to memorize? Yes, we'll learn that tomorrow. For now, we're going to learn it as the left AV valve, the left valve that separates the atrium from the ventricle. Now, the whole reason we pump blood is where do we need to send it from the left side of the heart? From the left side of the heart, it's going to go... So we're going to have to go into a big old blood vessel. Does anyone know the name of the big old blood vessel where all the blood leaves the heart to go everywhere? We have a big old blood vessel. It's big, and it's old. It's a blood vessel. It is the, maybe you've heard of this, maybe you haven't. The aorta. That's another blood vessel. And by the way, these are the arteries that branch off of the aorta. And we'll learn some specific artery names later. For now, enough to understand, all of your arteries that send blood around your body branch off of the big one. And this is kind of weird to think about, but your aorta, look here, it's a tube like this big. So think about that right now, like it's in your chest, big old pipe like this, and blood just flows through it. It's like you could like stick your thumb down it. Don't, because like you'd have to like cut your chest open. But like I'm saying, you could, if you cut your chest open, which we are going to not do. We're going to not do that. Okay, so now blood goes everywhere through the aorta. But of course, we need what? We need to make sure that as soon as the heart stops beating, as soon as the pump stops, what don't we want all the blood to do? We don't want it to fall back into the heart. So what do we need? We need a valve. And this one is the valve that makes sure that blood stays in the aorta. So we call it the aortic valve. Isn't that a good name? It's a good name. Aortic valve. Oh, except I don't color valves red. What color do I do valves? Yellow? Kind of yellowy, orangey. That color. So that is the aortic valve. Now, when blood goes everywhere, it goes to your toes. Your pinky toe full of blood right now. Your hair is not full of blood, but your hair follicles are. Your brain, your toes, your genitals, your everything, all of it, your stomach, your intestines, all full of blood. And then that blood needs to make its way back to the right atrium. Now, of course, blood can either come from the top half of your body or it can come from the bottom half of your body. So we need to account for both. So on top, we have the on top big vein. That's what that thing's called. Now it's called that in Latin. So does anyone know what it's called? It's the on top big vein. How do you say above in Latin? It's superior, and it's the superior vena, so vein, cava, cavernous, huge, big old thing. It's the big, huge cavernous vein from up top. And if that's the superior vena cava, what do you suppose we call the same thing that comes from the bottom of your body? The inferior vena cava. Very good. All right. Now, where do both of those lead? They lead to the right atrium. And of course, from the right atrium, blood's going to flow down into the, not the left ventricle, the right ventricle. Okay. Where's my blue? There it is. There's the right ventricle. It's just the way the picture is taken, but also this needs to be big because we are collecting a lot of blood here because it's coming from everywhere. This needs to be relatively big because it's sending blood everywhere. On the other hand, this is small because it's collecting blood only from the lungs, and this is smaller because it's sending blood only to the lungs. Does that make sense? So the two that are connected to everywhere are bigger, and the two that are connected to the lungs are smaller. Does that make sense? Cool. That was a great question, by the way. All right. Now, if we're going to go from the right atrium to the right ventricle, we got to make sure we don't go back up into the right atrium. So what are we going to have to pass through? A valve indeed. And what is this one called? Well, if that's the left atrioventricular valve, this one's going to be called the
right atrioventricular.
Very good. The right atrioventricular valve. The right atrioventricular valve. Now, does it also have a silly name we're going to learn tomorrow? It does. But this is its better name because it just tells you exactly what it is. It's the valve on the right side of the body that separates the atrium from the ventricle. Not a good name? I feel like if I name my second child, female daughter, born August 20th, 2007, Orlando. That'd be a good name. Have a good ring to it, right?
No.
Other than Pump, I'll tell you that much.
Why she still put Roger?
Oh, it's my last name. Last names are weird too, if you think about it. But I guess it makes sense, right? Tells you who you're related to. Yeah. But then it's like the whole male name thing. Like my wife took my name. We were married at like 22. I think like, boy, if we'd been married a few years later, like, and I don't think of her as Brittany Orlando. That's a stupid name. It's Brittany Culp. Like that's who I met. That's who I like fell in love with and married, right? So it's weird. You're like, by the way, now time to change your name. It's weird, right? Not weird. Why didn't I change my name? I could change my name. Like what stops me from being Joe Culp? It's as good a name as anything else. Maybe we just pick a new name. We could pick the last name together. We both could have been Joe and Brittany Pump. We wanted to. Nothing stopping it. Do you see what I'm saying? I'm just saying. Okay, now, where does the right ventricle send the blood? Right ventricle is going to beat, and it's going to send the blood where? Well, it's going to send it to the lungs. But of course, it's going to have to travel through some kind of tube. So what's the tube that goes to the lungs? Well, if these are the pulmonary veins, these are going to go to the lung. So we're going to call them the left pulmonary veins. Come back to the heart. What do we call the ones that leave the heart? Yeah, you do. They're called arteries. Yeah. Arteries leave the heart. Veins come back to the heart. Alphabetical.
Would that not be singular?
Oh, that is singular. Pardon me. I was busy talking. That is indeed singular. Yeah, there's two veins that come in from each side of the heart, but there's only one artery that leaves. So left pulmonary artery, and this would be the right. Yeah, I'm going to need more space than that. And of course, when we send the blood to the arteries, we need to make sure it doesn't come back into the heart. So what are we going to need? Another valve. And this one also has a nice name to it. It's called the pulmonary valve. Very good. Now, tomorrow you're going to learn that the atrioventricular valves are also called the mitral valve and the tricuspid valve. One because it has three cusps, and the other one, and this is true, because it kind of looks like the Pope's hat, which is called the mitre. Yeah, actually. It's called the mitral valve because it kind of sort of looks like the Pope's hat. That's a stupid name. Atrioventricular name? Good name. Valve that kind of looks like the Pope's hat? It's not a good name. It's a terrible name. But that's its official name, and you're going to learn it. Mitral valve. But do you see how everything on here has a perfectly normal function? And then here's a word you absolutely know. And this is not like a special heart word. This refers to any structure that separates two chambers. You might be familiar with this structure in your nose. What do we call tissue that separates a left and right chamber? Separates them, if you will. Some people get this of their nose pierced, but you wouldn't want to get this of your heart pierced. The septum. So septum isn't a heart-specific word. Anytime you have tissue that separates a left chamber from a right chamber, we can call the separating the septum. So this would be the cardiac septum, or the ventricular septum, if you like. Okay. I don't know. Sure. I mean, it's not really black. It's really like flesh-colored. But
Yeah, that is crazy.
Why is Angela catching strays
I
right
was
now?
so offended right now.
what?
Why is it not allowed to be black? Why is it not allowed to be black?
What color am I marking that? Yeah, did you say why?
Okay, guys, settle down. Good Lord. The answer to the question is because it's not a blood vessel, a chamber, or a valve. So I'm going to make another category, and we're going to call it structures, I guess. Structures, because we actually will get some more structures tomorrow, and we'll label them all with black ink. There we go. And nobody will take that as meaning anything because we're mature people who can use colored pencil crayons without turning it into some sort of fight. All right? Can we all agree on that? Good, I'm glad. We have, is it 05 or 10 after that?
10.
Oh, good, we got time then. Now, let's take a look at the bottom, just as an example. Now listen, you have lots of arteries in your body, lots of arteries. We're going to look at just the first three. Does that make sense? Where do all of your arteries come from? They all branch off the aorta. So all arteries are branches of the aorta. So you have one big tube that leaves the heart, and it branches all over. Let's learn the first three. Which direction are these pointing? All of these arteries are pointing up and to the right. And okay, shut up. So listen, what part of the body are they supplying? Do you think this one goes to your toes? No. Where do you think these two go? They supply blood to your head. Yeah, to your cranium, to your head. So, with that in mind, you can feel these two right here. Take your two fingers and put about 10 centimeters below your left ear, and you'll feel a pulse if you press a little bit, and if you're really quiet and still. Feel your pulse? Try it on the other side. You should be able to feel your pulse. You have two arteries that supply all the blood to your head, and they come up along the side of your neck. Does anyone know what they're called? Obviously, this one will be the left because things are switched, right? And this will be the right. But what are these two arteries called? You know it.
Carotid.
Yeah, carotid, carotid. The left carotid artery and I'm not going to write artery for any of these. These are all arteries. Is that fair? And we'll call this the right carotid artery. Does anyone know what the vein that goes down is called? Yeah, very good. Okay, but these are the arteries. The jugular would empty into the superior vena cava. The left and right carotid artery come from the aorta. What about this? So this supplies the head, right? And your head's important. We need that. Because what's in your head? A lot of stuff. Your tongue, taste receptors, your eyes, but notably, the brain. Big old brain of yours, and that's important. You need that. All right. Where does this one go? It feeds your arms, and those are important. Now, how does it get there? It runs under this bone right here. So you actually can't feel this one. This one runs under your collarbone, which you can feel. Does anyone know the collarbone's proper name? I'm going to throw my coffee at you. Does anyone know? Clavicle, very good. So this is called the sub, which means below, clavian, which refers to the clavicle, artery. And this supplies the arm. And this one is obviously the left subclavian. So it supplies the arm and upper torso. Your shoulder muscles, things like that, your pectoral muscles. And what about this one? This would obviously be called the right subclavian. But you'll notice something. Just the way it's built, and it has evolved this way. We think it has something to do with pressure regulation, which obviously the first pipe is going to be under the most pressure. But if you look, these two branch directly from the aorta. Can you see that? But the right carotid and the right subclavian actually branch off of each other, and they start out as a single artery. Can you see that? You see how these aren't the same? How on the left side, they come right off the aorta as separate arteries, but on the right side, they start together. So this section here is its own artery until it branches. So we have to give it a name. And what might we call it? Well, if I were calling it something, I would probably say it's on the right side, and I would want to say, I don't know, it's the right artery that supplies the head and the arm. And so you know what they call it? The right artery that supplies the head and the arm. But of course, they use the Latin words, which means the Latin word for your arm is your brachus, so the brachio, and the Latin word for your head is your cephalus, so cephalic. So it's the right brachiocephalic artery. And that will branch into the right subclavian and the right carotid, whereas the left carotid and the left subclavian branch directly from the aorta. The important thing to know here is that these are branches. By the way, even before any of those, we have these tiny little arteries. We'll talk about these later, but these are the cardiac arteries. What do they supply blood to? Something else that needs blood, even though it's full of it, the heart. The heart doesn't use the blood that's inside of it. It actually uses this blood here. All right, guys, take it easy. Have a wonderful day. Be kind to one another. If you're going out trick-or-treating, be respectful of your neighbors. Be nice to little kids. Don't do mean things to houses that don't give you candy. Stay safe. If you're going to a party, stay safe. Keep your drinks and things attended to. And we'll see you all tomorrow. And if you want candy on the way out, have it. Because if you don't, I'll just eat it all. And that's not good for anyone. Excellent. I'm glad to hear it.